Hey, Honors Physics, this is Mr. Hausman. We're on page number 6, which was one of your assignment pages, but you also notice at the bottom of 6, there's a section that begins something a little bit different. And so we're going to draw a little break in the action here, and we're going to just kind of separate. And what you hopefully noticed is that something new started on the bottom of 6. And what you might be able to not tell that these have in common is that we have metal objects. These are metal conductors that have charges on them. Here's one in which there's a positive and negative side. And maybe this is a continuous or empty, it's a continuous shell, but it has air or no charges in the middle of it. It's an empty shell. Here's a circular sphere, similar to what we might have seen in last chapter with the insulating base. Where the charges are on the outside skin. And then here, this is a little harder to see, so I'm just going to color it in, is something called a solenoid or a core. And it's a piece of conductor that kind of has, right, and what you hopefully can still see, is that it has a positive side, it has a negative side, but again, it's got a hole in the middle. And in every single one of these, you notice there is no electric field inside a conductor. So if it's filled with air or it's hollow or there's a center core, what we notice is that electric fields are always missing inside conductors. And to some degree, this has a name, and it's related to something called shielding, and we'll look at that. So how does electric fields change based on the distribution, right, of charges on a conductor? So the way it mostly works is that if you have a metal conductor, the charges only exist on the outside shell. So if this is like our metal spheres, right, the charges are never truly in the middle. Everything is happening on the outside. So we have negative on this side, positive on this side, maybe we have a polarization. And you notice that the electric field lines are coming into the negative side in that picture and out of the positive. The charges don't particularly move unless there's a reason such as an outside charge, so they kind of stay in place once they've been repositioned. Sorry, there was just a sound going off on my phone across the room. And inside, there is zero field, right? There is a region where the field lines don't go in, they don't go out, right? There's no field in the middle. So the E value is 0 in the center, okay? And anytime you put a metal sphere like this into an outside electric field, it's going to cause it to be polarized in exactly this way. It will kind of go inward toward the negative side and outward away from the positive side. My drawing is not perfect. We've got negatives on the left, quick reminder, and we've got positives on the right. I guess I'm trying to draw it in very fine detail. So that's what happens when conductors, such as a metal object, are put into an electric field. Now, furthermore, I hope you notice that on curved surfaces, the shape of the electric field line, right, is always perpendicular to the curvature of that surface. So it always points outward, away, perpendicular from the surface. And there are no components that are ever parallel to the surface. How do you do that? Well, you create perpendicular. So field lines are perpendicular to surface, never parallel to the surface. Now, what if it's an uneven surface or it's an irregular process? And again, I just want to make sure you're clear, right? The reason why this doesn't occur is because the E field would have a parallel component, and that just can't happen. So here are some uneven surfaces, and this explains some of the things that we might have seen in class. That the curvature or the shape of the surface of the metal conductor has a great deal to do with the strength of the E field. Notice on this wide curvature on this back side of this sphere, see how the field lines are spread out more. But when the radius of curvature is a little bit tighter, right, a little bit narrower, we have a higher field strength on one side to the other. And that explains some of the things that we've seen with the pointed metal or plastic rods that we've used. In this case, right, even the tip of a fingertip that's charged up has a much higher radius of curvature, so the field lines are kind of bunched up like that. And here's another random drawing that kind of shows kind of like a thumbtack, if you notice in the middle, and it has a very complex. If this is the shape of the metal object, its field line can get quite complex, but the rule is that it's always perpendicular to the surface. Now, let me introduce something that's referred to as a Faraday cage. What is a Faraday cage? It's a metal screen, and we're going to see one in class, that essentially shields or prevents a piece of equipment or any kind of research tool that basically can prevent any electrostatic or electromagnetic influences. So it's another region where there are no allowed E-fields. So what does it look like? It literally is, in the most basic sense, a cylinder made of like wire mesh. And what you can put in that could be maybe a very important medical device, and you don't want any interference from outside electric fields. It works by itself, but it would block outside influence. And that's really important. A metal mesh, right, between the glass and a door stops the microwaves from coming out. Have you ever looked carefully at your microwave door? You'll notice that you can see through it, but if you look really carefully, it's actually a metal panel with holes drilled in it very close together, and the hole spacing is made so that the microwave radiation stays inside, but yet visible light can pass through. And they have picked that spacing so that you get visible light and no microwaves going through. There's a new thing on the market where wallets that you can purchase also have mini mesh metal coverings in them, because credit card details are no longer just in the magnetic stripe on the back, right? The new kind of credit cards have a small chip in them that is in theory linked to you, and depending on the device that is brought near this credit card, it can read some of the details. Now, these credit card sniffers have to be very close to your wallet, but I suppose if you're standing someday in a crowded place and you carry a wallet in a pocket or a bag that's over your shoulder, someone could bump up against you, walk next to you, and scan your card. Most of you are used to the fact that cards get used in these new card readers that kind of look like this. And, maybe you put in your PIN code if it's a bank card, and there's a screen here, and you have to insert your credit card into the card reader, and that's not needed. The latest kinds of credit cards that many people are getting can be done wirelessly by tapping or being in close proximity. So Faraday cages are really important for protecting from interference from electric fields. Right. So let's look at the final combination of all of these ideas. So a cumulonimbus storm cloud has a bottom surface that's negative. That causes the ground below it also to polarize, and the surface closest to the cloud will become positive because, remember, the electrons are being pushed away by the cloud. And I've actually seen this happen with athletes out on the field during the spring, where their hair will stand up on end because they are standing inside this electric field. And it's incredibly dangerous, and that didn't last for very long before we decided to go inside. But essentially what you notice is that on a stormy, when there's an electrostatic storm in the neighborhood, there's an enormous E field being created, which means that if you put materials in it, they become kind of a little bit more staticky. So the E field of the atmosphere, not inside the cloud, but in the atmosphere, is from the positive to the negative. And now we're going to insert a metal object into this picture. So here's a car. I really need to take drawing lessons, right? I don't know what kind of car this is. And that metal car is a solid but hollow conductor, right? Oh, sorry, that didn't make sense. It's a hollow conductor because it has a metal skin to it. You may sit on the frame or the seats, but essentially the outside of the car is metal. And what happens to the electrons inside this field? Well, we actually have electrons drawn to the positive earth. Let's use green. And the protons are pushed in the direction of the electric field. So the car becomes polarized. We saw that on a previous page. And now the car creates its own electric field. And that's within the space. But a minute ago, you may have noticed that I said that the electric field cancels out. Well, for the same reasons we saw with parallel plates, the E field that's outside the car being upward and the E field that's inside the car being downward, they ultimately cancel each other out. They are combining together to get a region of no electric field inside the car. So I hope you have a better understanding of why cars are safe. You are told by a lot of parents and coaches and even safety experts that say cars are safe because they have rubber insulating tires. And that's not at all why this is true. The rubber tires may prevent maybe a small amount of contact with the ground, but electrons can still travel down through a stepped leader and ultimately reach up to a streamer, and the electrons can come through and hit your car, but they won't go inside the car. The electrons would go down and around. And this is referred to, the canceling out of electric fields and this protection, as electromagnetic shielding. So a little background on lightning and how it relates to charges in an electric field. Interlude about lightning. So lightning is really cool. It's fascinating. There's some great NOVA videos on lightning that are quite long. And we've decided this year that a 54-minute video in class takes up multiple class periods. But what lightning is essentially a buildup or a strong electric field inside a cloud that it basically gives so much energy to the charges that they tend to have to go somewhere. So there's a strong field in a storm cloud, and we're going to examine how that works. So this is a little bit of detail. So we believe that lightning is created by the collision of ice crystals and water molecules. And so there's some friction inside a cloud. Clouds have vertical updrafts and downdrafts, and the rubbing together of these ice crystals creates a separation of charges. And it's well documented when they send sensors up, like weather balloons, into these clouds, that the top surface of the clouds are positive and the bottom surfaces are more or less negative. And that creates an E field. It also creates an electric field with the Earth, because the bottom of the cloud causes the top surface of the Earth, the trees, the ground, or a car, to become more positive. And what you get is another electric field. Now this time, the E field that's in the cloud is downward, but the E field that's in the atmosphere, the space between the ground and the cloud, remember it always goes from positive to negative, and it's pointing upwards. I know the Earth looks curved, but we're going to say it's a flat ground. So here's another E field. There's the E field inside the cloud, and then the E field on the planet. And when those electrons encounter that E field, the electrons move downward against the E field, and that makes sense if you think about it. They're attracted to the positive ground, but they do it in what's called a stepped leader. They branch and they find the easiest path down to the Earth, the path of least resistance. And it can be many meters long, 30 meters in length, but when it reaches a positive streamer, and this is not the best picture, but it kind of has it all on one page, when the stepped leader meets a positive streamer that comes up from the ground, it connects, And the lightning, right, is created by the discharge of the electrons moving to ground. Here come the electrons moving to ground. And it's incredibly powerful, and it's beautiful, and it's really cool if you're a safe distance away. And on the left, I think there's a page of this. We're going to kind of look at how to protect yourself, okay? Here's another version of kind of what is lightning. And this cloud has, clearly negative bottom, positive top. These are sometimes called anvil clouds because the top of the cloud structure kind of has a huge kind of protruding front edge. And they've now found out that even though the cloud may not be very thick right here, the electric fields inside the cloud are huge. And that, again, causes the surface of the earth. So along comes your car. And maybe you've heard that cars are safe when it comes to lightning. And that's actually very true. Because what happens if you park your car inside this electric field, the one that's between the earth and the storm cloud, is that, right? Remember, the earth is positive, and the cloud or the bottom surface of the cloud is negative. And here's your metal car. It's essentially a hollow metal cylinder, right? And it has a metal skin. And look what happens is that the car becomes polarized, but becomes polarized the opposite direction, right? The E field from the earth up goes from the earth to the cloud. It does get bent slightly by this metal object. Remember, we talked about metal objects in electric fields. But look what happens is that the car's surface, the skin, the metal skin, is actually a hollow conductor, and it has an opposite field, and that is going to create a region, and I know that's it may be a contradiction, they cancel each other out. So there's no E field inside your car. So what is the chance of the electrons coming down from the cloud go right through your car and right through you? And the answer is next to none. They could hit your car and travel through the metal, but they tend not to, okay?